All right, welcome to the second part of Chapter 6. This lecture concerns enzymes. We're going to talk about enzyme structure and function. We're going to look at something called the induced fit model. We're going to compare cofactors and coenzymes and what their role is in helping enzymes to function. Then we're going to look at the effect of temperature, pH, and substrate concentration on enzyme activity. We're going to compare a variety of inhibition things that can stop an enzyme, competitive and non-competitive inhibition, and then finally feedback inhibition. All right, so first recall from the previous lecture that chemical reactions do not proceed spontaneously, and this is really important. We don't want reactions to occur when we don't want them occurring. We don't want to build product we don't need. In fact, if you ever watch the pharmaceutical ads on TV, one of the things they'll tell you to watch out for is unexplained weight loss. When you lose weight without trying, it's because you have chemical reactions proceeding in your body that are not being controlled, and you're burning energy that you don't want to burn. It's like, you don't when you go someplace where you're going to be there for a while, you don't leave your car running because you're wasting gas. And the same thing is true in your body. If you're building products you don't need, then you're wasting energy. And so one thing that happens is we've got that activation energy barrier that keeps reactions from proceeding until we invest that kind of energy. Now in a chem lab, we can easily invest that kind of energy and it's no big deal. But in your cells, if we invest all that activation energy, there's a good chance that much energy is going to cause damage to the cells. And so that's how cells control making product, right? They can't give themselves that much energy or it damages the cell, right? So the reaction doesn't proceed. Okay, and again, that's activation energy, or the energy of activation, EA. And recall in a previous lecture that catalysts, one of their jobs is to lower the amount of activation energy that's needed before the reaction can proceed. If we look at this diagram, here are reactants, here are products. Now, without an enzyme present, we've got to add this much energy. And that much energy is probably going to be harmful to the cell. The reaction just isn't going to happen in a cell. But with the enzyme present, look, we need half the energy. We need half the energy for this to proceed. And now we can add that. The reaction proceeds and not damages the cell. Okay, so that's what catalysts do. Catalysts lower the amount of activation energy needed for the reaction to proceed. Most of the time, they're proteins called enzymes. But there are some catalytic pieces of RNA we're going to see much later in the semester that we're going to call ribozymes that also are capable of catalyzing chemical reactions. Enzymes are proteins, so again, from way back in Chapter 3, recall your 4 structures of a protein: primary, secondary, tertiary, and quaternary. And when we put them all together, remember it gave an enzyme or protein a unique three-dimensional shape. And when you have a unique three-dimensional shape and you're an enzyme, part of that shape is something called the active site. And this is where the substrate binds. The substrate is whatever the enzyme's going to act upon to cause a reaction to occur. So you could also think of the substrate as being reactants. In some reactions, there's a single substrate that's going to be separated. In other reactions, there may be 2 substrates or more that are going to be put together to build something bigger. So it depends on the type of reaction on how many different substrates there are, but they're all going to fit on a physical spot on the enzyme called the active site. Right, and one way to think about it, if you've ever played baseball or softball, right, and you know that you need to have a glove that fits your hand. So if you're right-handed, you want a glove that fits on your left hand. If you're left-handed, you want a glove that fits on your right hand. And I remember back in elementary school when we'd play softball, and they'd have the box of school gloves, and if there were too many left-handed kids in the class, somebody probably didn't get a glove, or they had to use a right-handed glove on their left hand, and that really didn't work out that well. And the same thing is true of the substrate. The only place it can bind on the enzyme for the reaction to be catalyzed is the active site. Okay, and it's highly specific. An enzyme can only catalyze a single reaction because it can only recognize, bind to, and act upon a single substrate. This is a three-dimensional image of an enzyme active site. Remember, your protein has a three-dimensional structure. Only part of it is going to be the active site. There's also going to be next to that what's called the catalytic site, which is going to reduce the chemical activation energy needed for this reaction to proceed. Now, the induced fit model it replaces the old lock and key model. The idea was before the substrate and the enzyme were kind of like a key fitting into a lock, where the key was the substrate and the lock was the enzyme. And if you've got your car or your house or apartment or whatever, you know that you have keys that will only open certain locks. And it's a physical fit, but it's an exact physical fit. And if you modify the key too much, it may not fit the lock anymore. Okay? If the key gets worn down, you have to go get a replacement key, or if the key breaks. In the induced fit model, the substrate and enzyme don't fit real tight at first. It isn't a perfect fit at first. But because the substrate gets to this point, it now it changes the internal bonding patterns of the protein and causes it to change shape to fit the substrate really well. The substrate induces the protein to change its shape. Anything that gets close and can partially bind to a protein is going to modify its internal bonding patterns and cause this to occur. And if it's happening at the active site by the substrate, then we call this the induced fit model. And so we start with the enzyme and substrate separate. We have an enzyme substrate complex. This causes the induced fit, allows the enzyme to catalyze a reaction. We briefly have an enzyme product complex until the product is released and the enzyme returns to its former shape. Okay, notice that the enzyme isn't part of the product. It's going to be unchanged when the reaction is over. It's only going to change during the part of the reaction where it's catalyzing the reaction. Now, sometimes enzymes can do all this on their own, but other times they need help. And what that help is going to do is modify the active site to better fit the substrate. And there are several types of molecules or ions that can do this, and we usually break them into cofactors and coenzymes. Cofactors historically has meant metal ions, and these are going to bind tightly to our enzyme, and they're going to modify its shape because metal ions they're cations, they have a positive charge. And when that shape gets modified, the active site changes to better fit the substrate. Coenzymes are organic molecules, often derivative of vitamins, that are not as tightly bound to the enzyme. And sometimes they'll actually act as a co-substrate, and they'll get changed a little bit during the course of the reaction to become a product. Okay, but both of these cofactors, coenzymes, modify the active site to better fit the substrate. And in enzymes that require that, the protein part by itself is called the apoenzyme. And then once we add the cofactor and or coenzyme, now the whole complex we call the holoenzyme, which is the fully functional enzyme. There are other factors that can regulate enzyme activity. Temperature is a good one. What determines whether or not the substrate binds at the active site? It isn't like the enzyme is trying to find the substrate or the substrate's trying to find the enzyme. You have substrate in the cytoplasm, you have the enzyme in the cytoplasm, and they're moving around because all the molecules in the cytoplasm have energy. And so they're moving around. And as they're moving, eventually there's going to be a chance collision, and the enzyme is going to meet with the substrate at the active site, and the reaction will be catalyzed. Now, we can increase the likelihood of that happening or decrease the likelihood by changing the temperature. If we start at a low temperature, the lower the temperature, the less movement in the molecules. But as we increase temperature and they start moving more quickly, then we increase, here's enzyme activity, this is temperature. As we increase temperature, we're increasing enzyme activity until we get to something called the optimum temperature. Now, in your body, your body temperature is 37 degrees Celsius on average. So this particular enzyme is an enzyme that would function best at your cellular temperatures. It might not be one of yours. It could be an enzyme in a bacteria that lives inside of you that grows best at 37 too. Okay? But this is the optimum temperature. Okay? And that's where the enzyme's functioning the best. If we take heat energy away, we're going to slow that enzyme down. We're not going to damage it, we're just going to slow it down. If we add too much heat energy, though, we can very quickly break down the enzyme activity. And what happens as you add too much heat energy is denaturation occurs. In denaturation, we take away secondary, tertiary, and quaternary structure. So all that's left is our chain of amino acids, our polypeptide chain. And you can see that here. Here's our three-dimensional structure, which is an active or functional protein. When we denature it, we take away the secondary, tertiary, and there's no quaternary structure in this one, but we take those away. Now it's just a string of polypeptide chain, string of amino acids, and it's lost its function. Once denaturation occurs, the enzyme can't be repaired. Okay, it's all done. Now, this is what happens when you cook an egg, right? If you've ever eaten a raw egg, this was popular back in the 70s. The movie Pumping Iron came out with Lou Ferrigno and Arnold Schwarzenegger, and all of a sudden, a lot of athletes started weight training, and they started packing extra protein into their diet. And one way to get extra protein was to eat raw eggs. I don't know why raw, but that was the thing for a while. And if you've ever eaten a raw egg, and I have, the yolk is a horribly bitter thing, and it doesn't want to go down in one easy swallow. It just kind of slowly uses its way down. A much better thing to do is to cook the egg, because when you get to a high enough temperature, you denature the proteins in the egg, and now we turn the egg white into a rubbery goodness, and the yolk is a creamy golden goodness, and we change the texture and the flavor by denaturing the proteins. Okay, pH will also cause denaturation to occur. All enzymes are going to have an optimum pH. They're going to have a pH that they work best at, and this one is right about neutral. Right around 7. And as we go below and above, now we're adding a lot of ions, H plus ions down here, OH minus ions at the top. And what's going to happen is those are going to cause any of the hydrogen bonds or ionic bonds or disulfide bonds, hydrophilic attractions that give the protein its secondary, tertiary, and quaternary structure to come apart, and now we denature the protein. Okay, so we can denature proteins by changing the pH. And this is what happens when they make cheese, right? They take milk, and inside the milk is the protein casein, and what they do is they add rennin, which is an enzyme which functions best at a lower pH, or you can do the same thing by adding a weak acid, like you can do this with milk. You can take milk and add orange juice to it, and you can see the milk protein fall out of solution. And in cheese making, that would become the curd that they're going to press the moisture out of to make the cheese. And then the whey, which is the lipids and the carbohydrates, usually they extract that and they can dehydrate that, and they grind it up and they use it as an additive for animal feeds a lot of the time, unless you're Little Miss Muffet and then you eat your curds and whey. But the last thing that can influence enzyme activity is substrate concentration. All right, so if we don't have very much substrate, our enzyme's not making product because there's no substrate. But as we start to increase the amount of substrate present, then there's a better likelihood that the enzyme's active site is filled with a substrate molecule. Now, all enzymes have what's called a turnover number, which is the maximum number of substrate molecules that they can catalyze in a given time period. And so for some enzymes, it's very large. It might be 100,000 per second. Okay. Others, it's much smaller, 100 to 1,000 per second. And so as we're adding substrate, depending on our enzyme, we're going to get to the point where it doesn't matter how much more substrate we add, we can't make the enzyme go any faster because it's functioning just as fast as it can. As soon as the active site is empty, another substrate molecule is there, and it doesn't matter how many more substrate molecules we add, the enzyme can't work any faster. Okay, it's like Santa at the mall, right? If it's in the middle of the day when most of the kids are in school and the parents are working, there's not very many kids that want to sit on Santa's lap. And so as soon as a kid leaves, there's a kid can get in right away if he's in line. But when you get past the dinner hour and everybody goes to the mall and kids are out of school, and now there's a big long line, it doesn't matter how many kids you put in the line, Santa's not going to move any faster. And there's a limit on how many kids per hour he's going to be able to sit with. And same thing is true with an enzyme. Saturation point is when we've got the enzyme working as fast as it can, and it doesn't matter how much extra substrate we add. There are also inhibitors that can block enzyme activity. And the two we're going to look at here are competitive inhibition and non-competitive inhibition. So here's our normal enzyme, here's our normal protein, and here's our active site, and here's our substrate. Okay, and the substrate is designed to fit the active site. And if the substrate binds to the enzyme at the active site, the reaction is going to proceed. Okay, but what if something else can bind to the active site? What if something else can bind temporarily and block the active site? Now, the substrate can't bind, right? This is in the way, and a lot of drugs. We're going to see this later, but a lot of drugs act as competitive inhibitors, and we'll talk about that again a little later. In non-competitive inhibition, instead of something blocking the active site, something's going to bind at another spot on the enzyme called the non-competitive or allosteric site. And when this allosteric inhibitor or non-competitive inhibitor binds, it causes the internal bonding patterns of the protein to change, and now the active site temporarily goes away. And now the substrate can't fit. There's nothing blocking the active site. There isn't an active site because the protein has changed its shape. Now, both of these are reversible. As soon as this competitive inhibitor kicks off, or as soon as this non-competitive inhibitor kicks off, then the enzyme active site restores or is empty, and now if substrate is the first thing there, then the reaction can proceed. Okay, and again, many drugs or pesticides or poisons act by targeting enzymes, and this is a big part of drug therapy. You know, if we're trying to control a symptom or a disease, or like regulate your blood pressure, or ibuprofen to control pain, or some antidepressants. You know, there are certain chemical reactions that are producing a product that can increase your depression. HIV, the virus HIV, virus HIV, the disease AIDS, protease inhibitors can help slow down that disease. Many of these work as a competitive inhibitor or non-competitive inhibitor, where they bind for a period of time, and of course a big part of drug development is identifying. Once we find something that can act as an inhibitor, first we have to find out whether or not it's safe. So there will be a small group of volunteers, 100 people, who are going to take very trace amounts and then a little bit more and a little bit more and a little bit more of the drug until they start to have a negative effect, and they identify how much is safe to use. And then they have to identify how much is necessary in order to get the desired outcome, whether it's to inhibit pain or fix your blood pressure or stop your antidepressant or stop your depression or whatever. And so those are called the pharmacokinetics and pharmacodynamics of developing a drug, and that takes time. And then they're going to test it on an animal model or some tissue culture, and then they're going to move into phase 3, which is where they actually put it out there, and they take 1,000 to 10,000 people and they run a trial. Okay, now to do those first 3 phases often takes 8 to 10 years. Okay, unless they fast track something because it's designed to fight something really serious, like a highly aggressive breast cancer or something like that. And this is one of the reasons drugs are expensive, because it's an awful time-consuming and involved process in identifying which drugs are going to act as inhibitors to which enzymes, how long they're going to last. Whether this one says take every 8 hours, some it's every 4, some it's 2, because it's, in this case with this drug, it's going to take 8 hours for you to clear it from your system. Is it cleared in your liver? Is it cleared in your kidneys? And you lose it in the urine, right? Is it metabolized somewhere else for energy? That's all part of the development of the drug and the testing of the drug to make sure it's safe. Most drugs don't make it through that. Okay, they aren't capable of being safe at the dose you need to do whatever they're going to do. There are also some pesticides and poisons that act as enzyme inhibitors. And of course, one of our concerns is chemical warfare. We want to, we don't want to develop something that can be abused. And when you see all the weird things that go on in society, what would it take for somebody to get their hands on a chemical that was deadly as an enzyme inhibitor and could get in a drinking water supply and poison a whole bunch of people. So we got to be real careful when we develop these kind of things so that they don't end up in the wrong hands. The last type of inhibition we want to look at is feedback inhibition. And remember from the last lecture that many reactions, and in fact almost all reactions, are part of metabolic pathways. They're a slow, gradual change from what our initial substrate is to our final product. And in the example pathway down below, you see there are 4 enzymes. And we start with an initial substrate. And the first enzyme is going to convert that to a product. But it's not the final product. So we're going to call that an intermediate B, which is a substrate for enzyme 2. And it converts it to intermediate C, which is a substrate for enzyme 3, which converts it to intermediate D, which is a substrate for enzyme 4, which makes our final product. Okay? And the reason for this is to change from A to the final product is probably going to require too much energy and be harmful to the cell. So a slow, gradual change through a series of reactions. Now, one way we can control the pathway is let's let the final product be a non-competitive inhibitor so that when this binds here, it changes the active site so it can't bind to A. And that shuts down the pathway. Okay? And this is how an awful lot of our metabolic pathways are controlled in our cells, is with feedback inhibition. This keeps us from making too much product. And so as we're using up the product, eventually we need the one that's bound here. Once it's off, the active site restores itself, A binds, and the pathway can proceed. And you say, well, why shut it off here at enzyme 1? Why not enzyme 2, 3, or 4? Well, if we shut it off down here, we still build intermediates. We're wasting energy building intermediates we might not need. And some of these intermediates, as they accumulate, might be toxic to the cell. So it's better to shut it down at the first enzyme. Okay, so discussion question. Which of the following is true? Which of the following is true? Non-competitive inhibitors change the shape of the active site. Competitive inhibitors change the shape of the active site. Non-competitive inhibitors function better at low pH values. Competitive inhibitors cause the enzyme to denature. So you can pause the video, take a few seconds, think about it, make your choice. Okay. Non-competitive inhibitors can't function better at low pH values because at low pH our enzyme is going to denature. And there's no point in inhibiting it because it isn't going to be active. And if competitive inhibitors cause the enzyme to denature, again, there's no sense in having an inhibitor because now the enzyme's denatured. Once it's denatured, it can't be fixed. It's gone. So C and D can't be the possible answers. Competitive inhibitors occupy the active site. It's non-competitive inhibitors that change the shape of the active site. So the correct answer was A. And so that's the end of the second part of Chapter 6. These are the key terms that you should be ready for on the exam. Nice short list this time. And then these are the key concepts that you should be able to address on the exam.